Hello, my name is Urvi Chakraborty. Here's my Lab 3 video. Lab 3 is about the magnetic field of a bar magnet. Just as an introduction to this lab, the purpose was to measure the magnetic field of a bar magnet. Some basic concepts that we covered was the Biot-Savart law, magnetic fields, magnetic dipoles, and some general procedures that we followed in this lab was to find um, where the magnitude of B of x using our magnetometer, measured to these following Teslas. We recorded the distance of each. Then we used all of that data to make a plot. This observation was to help find the distance dependence of the magnetic field of a bar magnet. We also used code to measure off-axis magnetic field, aka what the magnetic field would be from the magnet at a 45-degree angle. Um, we also found d perpendicular by seeing where on the axis um, the net B would be equal to 100 microteslas. So over here we see the different measurements that I found in the first part of the lab, where we had to measure the distance at which the net magnetic field would be 20 microteslas. Um, after recording all of this data, we found the averages of each, and with these averages we plotted onto this plot here on the right. As you can see from the measurements that we did on the previous slide, you can see that the closer you are to the magnet, the larger the B of x value is going to be. When we put all of that measurement onto a plot, we found an equation, a linear equation that basically equates to the natural log of B of x equals to the natural log of k minus the natural log of r times the n value. So since the natural log of k is equal to the y-intercept in the plot, we get minus 17.001 for the natural log of k. For the n value, it's the slope of the equation, so it's going to be minus 4.5779. So this value is a bit off from what the expected value would be, which is -3. It's just a bit bigger, but using all of these values that we found from above, we can use that to solve for both the magnitude of the unit vector as well as the mu value that would be found in the Biot-Savart law, as shown on the left over here, using the b-axis formula right over here. So the mu value ends up being 0.206, and we end up using that for our code. Now looking at the second part of the lab, we had to code we had to both code and measure what the magnetic field off axis would be for this bar magnet. So in the code, we created a function that was based on the formula over here on the right. Using the calculated mu value that we found in the previous part of the lab, we created two different arrows representing B on the axis. We created arrows representing B perpendicular to the axis, and we created a whole bunch of arrows representing B off axis on a 45-degree angle. So over here we see that the arrows on the axis is the orange ones. Perpendicular to the axis is the blue ones, and then the ones off axis is found over here with the magnetic field. When we compare the actual experiment to the simulation, we find that the experiment values and the code values are pretty different from what they're supposed to be. Some systemic errors that may have been used um, to contribute to these errors is mainly the fact that my hands are very shaky and it causes me to bump the phone at times. So that probably influenced what the values of Bx would be in By and Bc. The magnetometer being influenced by the computer, by my laptop and computer nearby, as well as other metal objects in the surrounding area. They weren't close by. I tried to make sure, but it still could have impacted the values, as well as the fact that the n value that we found in the first part of the experiment that was larger than expected, and I used that for some of my calculations in order to find mu. So, because of these influences, um, that could probably account for the differences in the numbers. If we hadn't accounted for the Earth's magnetic field in our setup, the numbers that we would have for the X, Y, and Z would be pretty askew. So because of the Earth's magnetic field, it will affect the direction in which the X, Y, and Z of the magnetic field that we are calculating for. And if we had two identical magnets and we redid the experiment, when you combine these two magnets together, you'd probably have a positive and a negative side of the magnet being attracted to each other. And on the other side, you'd have negative and positive being forced apart from each other. So that would probably switch the direction in which the magnetic field on axis would be pointing. So instead of positive or negative by, bx, um, we would have we'd have the opposite sign.